Hello everyone. Today we want to discuss how to graph a rational function. So then a rational function. So the first thing we have to know is what a rational function is. So rational function is a function of polynomials. So if we have polynomials over another polynomials, so then this function called a rational function, which is a kind of fractional function. So we have to learn how we can graph such function. So then we have to take several steps. So step one is, so we have to know what would be the domain of that function. So then first is finding the domain. So for example, if I have f of x equals to x plus 1 divided by x minus 2, so domain, which all we know this, right? So domain is all possible x values. So then what kind of value we allowed to take for this x here, so in this function? So as you know, any real number would work here except those numbers making the denominator 0, which causing my rational function undefined. So then if I have x minus 2 is 0, that is undefined, so we're not allowed to take that x. So then x is going to be equal to 2, which is so we're not allowed to take that x on this function. So then domain of this function is going to be any real number except 2. So then this is domain of this function. So the second step, so step 2 is finding any possible asymptotes. So the first thing we have to know is what an asymptote is. So asymptote is a line, so it's a line or a curve which function approaching to, so the function approaching to, however, so not allowed to cross or touch. So I'm gonna put just one star here. We're gonna come back to this topic later. So then for to find any asymptote, I have to take several steps. So then step A, so if there is any common factor, so common factor between the numerator and the denominator. So for example, if I have f of x equals x squared minus 1 divided by x minus 1. So if I have such a rational function, so as soon as I see any, I look at any rational function, so I have to check this like step 2 part A first before I do anything else. So if there is any common factor between the numerator and denominator, like as we have here, so in this case I have x squared minus 1 squared. Then as you all know, this is going to be x minus 1 multiplied by x plus 1 divided by x minus 1. So if I have a common factor, so then these two common, this common factor will be cancelled out, and then this function is going to be x plus 1. So then my f of x is going to be x plus 1, which is like linear function. However, as you know, the first step was finding the domain of the function, and then as you can see, if you look at this function, so domain would be R except like any real number except 1. Why? Because 1 will make this rational function undefined, as that makes the denominator 0. So then if I have any common factor, so I have to cancel them out first. So then, for example, for this function, so then we're gonna have, like if I want to graph this function for you, so we'll have something like this. If I have, imagine this is positive 1, then I have like that function is like this, which is x plus 1. However, we said we're not allowed to take x equals to 1 because it's not a possible value for x. So then if I have x here positive 1, then this point is not allowed to be on the function. So then I have to have a hole here. So then if I have any common factor between the numerator and the denominator, then we could expect having a hole on the graph. So then this is step 2 part A. Now let's have the second step, which I call that part B. And then if I have any rational function in this general form, if I have like a x raised to b plus c, and then over like dx raised to e plus f, like if I have a rational function in this general form, then we have several options for any possible asymptotes. So then I have to check the power of leading term. What is the leading term? So leading term in polynomials, leading term is that term. So leading term is that term which has the highest power in polynomials. So then in this case, this is going to be my leading term and in the numerator, and then also I have this as the leading term in the denominator. Now, if I compare the power of the leading terms, so then comparing the power of the leading terms, then I have 3 possible options. So then if B is smaller than E, so it means if the power of the leading term, the numerator, is smaller than the power of the leading term in the denominator. So in this case, we'll have a horizontal asymptote and then how would be that horizontal? So then y equals to 0 is going to be that horizontal asymptote, which is x-axis. So then x-axis would be the horizontal asymptote for such function. Now, if b equals to e, so it means the power of the leading term in the numerator equals to the power of the leading term in the denominator. So in this case, we still have horizontal asymptote. However, that horizontal asymptote will be the coefficient of the leading term in the numerator over the coefficient of the leading term in the denominator. So then I'll have a over d as the horizontal asymptote. And then the last option is going to be if b is bigger than e. So then in this case, so I have to check another option also. If b is bigger than e and if b minus e is only 1 unit, so it means I have the power of the leading term in the numerator is bigger, only 1 unit, than the power of the leading term in the denominator, then we'll have oblique asymptote, which is oblique asymptote. So then I call this OA. Like some textbooks also call that as a slant asymptote. So then all the same. And then how can I find that oblique asymptote? So it's very easy. So I have to calculate. So then for this oblique asymptote, it's going to be ax raised to b plus c long division by dxe plus f. So then you have to calculate this long division. If you don't know how to do it, you can put a comment for me. And then, so I'm gonna explain that long division in another session. That is also very easy. Okay, so then this is so this is part B of the second step. So and also I have to check another possible asymptote. So then if I look at this, so then I call this part C. Then so part C is going to be any possible vertical asymptote. Which is VA. And what would be vertical asymptote? So vertical asymptotes are those numbers making my denominator 0, which that causing my rational function is undefined. So then in another word, if I have so any roots of the denominator will be those vertical asymptotes. So then we're gonna discuss, I'm gonna give you some examples later on, and then I'll understand those things better. So then this is step 2. So let's have step 3. So step 3. So behavior of the function. So I want to know how that function behaves at two important regions. So then I have to check behavior. So then A is ending behavior. So we want to know like any rational function, how does any rational function behave generally? So for example, so imagine I have like f of x equals to x over x squared minus 1. So as an example, so then if I want to know how would be ending behavior, so I have to take the leading terms from the numerator, which is x in this case, divided by the leading term in the denominator, which is x squared in this case. So then it's going to be 1 over x. So then that means if I want to know how would be the ending behavior of this function, so then I'm going to show that on a graph, then so would be better for you. So imagine so as you know, this is quadrant 1, this is quadrant 2, this is quadrant 3, and then this is quadrant 4. Okay, so what can I do by having like the ratio of the leading terms? So I know in Q1, so x all positive number, so then I have x positive, and also I have y positive number. So let's have this, probably would be better. So x all positive number, and then y also any positive numbers. For Q2, x is going to be a negative number, so then negative number, however y still is positive. In Q3, x and y both are negative, so then x is going to be a negative number, and then y also is a negative number. And for Q4, I have x all positive numbers, however y is a negative numbers. So then if I want to know, so this is a rule for like every single rational function. So then if I want to know how that function behaves as the ending behavior, so if you have 1 over x here, so this is 1 over x, so then if I have x a very big number, like for example if I have x equals to 1 million, so then do you agree y in this case, y is going to be almost 1 over 1 million, which is very small number. So then I have x positive, y is still positive, so then it means one of the ending of my function is going to be in Q1, so then I call that E1 as ending 1. And then now imagine if I have x equals negative 1 million, which is a negative number, and then how would be y? So then y is going to be almost 1 over 1 million, but negative 1 over 1 million. So then I have a negative and negative. So then it means another ending behavior of my function is going to be in Q3. So then I call this E2 as the second ending behavior. So then it means if I want to graph such function is like this function, so I have to know how would be the ending behavior of that function. And the other thing, so the second type of behavior we have to know in this case is behavior around the asymptotes. So then based on the rules we discussed here, then if you look at this function, so I have the top power, the power of the leading term in the numerator is smaller than the power of the leading term in the denominator. So that means I have a horizontal asymptote, and what would be that horizontal asymptote? That is going to be y equals to 0. So then y equals to 0 is going to be horizontal asymptote in this case. And is there any vertical asymptotes? Probably. So I have to check all those roots of the denominator. So then I have to check for vertical asymptotes. So I have to find the roots of the denominator. So then it means if I have x squared minus 1 equals to 0, then x squared is going to be equal to positive 1, and then I have 2x, I have two roots. X is going to be positive 1 or x is going to be negative 1. So then these two are my vertical asymptotes. So then there is a key point for any asymptotes, which is very important in this case, like in rational function. So then I'm gonna write down those things with red color. So then the key point is this. So vertical asymptotes not allowed to cross or touch so let's have this better. Okay, so there is a key point here. So the key point is this: the function not allowed to touch or cross vertical asymptotes at all. However, so the function might be allowed to touch or cross horizontal asymptote or oblique asymptote at some few points. So then this is very important key point here. So then in this case, so I'm gonna take this function to the next page. So then I have more space here to explain better. So then fx is gonna be x over x squared minus 1. Okay, so then we said there is vertical asymptote, which is x equals to positive 1, and then x equals to negative 1. And also there is horizontal asymptote, which is x-axis. So then that is x-axis. Okay, so if I want to graph this function just for now, so I have let's have this also here. Okay, so we said there is positive 1 and then negative 1 for the horizontal asymptote. So then I'm gonna color that horizontal asymptote with a red line. So then these two are vertical asymptotes. So why I draw that with the red color? Because we not allowed, I mean the function not allowed to touch or cross at all. But so I have another asymptote, which is horizontal asymptote. So then I'm gonna use blue color, because at some point the function would be allowed to touch or cross the horizontal asymptote at some few points. Okay, so we said we have E1, like one of the ending points would be on like in the first quadrant, and the other one is in Q3. We discussed that in the previous slide here, right? Okay. Now, so then I have positive and positive here, and we said if I have a big number, then y is gonna be, this is x, and then this is y. So then it's gonna be like this very small y would be for a big x. So then the other one is going to be for a big negative x. Y is going to be very small number. So then I have something like these 2 points. So like this point and then this point, which is in Q1 and Q3. Okay. So the other thing we discussed is the behavior around the asymptote. So then I want to know, how does this function behave around the asymptote? So then how can I know that? For example, so 1 and positive 1 and negative 1 are those points which we're not allowed to take those points for the original function, which is this. But I can check around these numbers. Like if I have, for example, if I have so let's have like positive 2, for example. So if I have positive 2, so then if I want to calculate f at 2, so then this is going to be 2 divided by 2 squared minus 1, which is going to be 2 over 3, right? So then if I have 2 over 3, so then I have, for example, if this is 1, so let's have this is positive 1, so then 2 over 3 is going to be like a point like this, so like here, right? So then if I have any like smaller point, then like as long as I approach to this positive 1, the graph, I mean the y amount is getting bigger and bigger. So then I can know how would be the behavior of this function from this area, from like this region to, I mean, around the vertical asymptote. Okay, now if I want to graph this region of this graph, then that is going to be something like this. So it's going to be something like this. Why? Because so I knew this, right? As long as we approaching the numbers, I mean, we're approaching to +1, y is getting bigger, bigger, bigger. And I know we're not allowed to touch at all this +1. So then the function will go to infinite. I mean, the y amount will be a lot bigger, because that doesn't, I mean, it's not allowed to touch or cross this asymptote here. Now, if I have, so for the other ending behavior, so I have like this point, and now let's have this like -2 here. So -2. So then if I want to calculate f of -2, then it's going to be -2 over -2 square minus 1. So then I have -2 over 3. So which is so if you look at this also, for any x, so we'll discuss that here. So for any x, if x is negative, then y is going to be a negative number. So then I have -2 over 3. So imagine this is -1, and then this is going to be almost -2 over 3, so which is this point. So then it means if I want to graph this region of this function, so we'll have something like this, and there's this graph is not touching or crossing this asymptote, this vertical asymptote. Okay, so these are ending behavior of that function. But so the other behavior we said we need, so we need to have is behavior around the asymptotes. So then let's have this around asymptote. So I have so one area, so let's have like this area here, this region. So for this region I have the region between those two vertical asymptotes. So then I'm pretty sure the function not touching or crossing the vertical asymptote at these 2 points, this point and then this point, then there is no other options rather than the function has something in this region, so like in this region. So then how would be that? So for example, if I have -1 over 2, so this is -1 over 2. If I want to calculate f of -1 over 2, so then I have -1 over 2 divided by -1 over 2 square minus 1. So then I'll take this here. So then I have -1 over 2 divided by 1 over 4 minus 4 over 4. Like I have 1, which is 4 over 4 is exactly the same. So then that is, -1 over 2 divided by, so -3 over 4, which this negative will be cancelled out. And then, as you know, if I have two fractions divided by each other, then these two like farther numbers multiple by each, and then these two closer, multiple by each. So then it's gonna be 4 over 2 times 3, which is 4 over 6, which is 2 over 3. But that is a positive. So then it means, and positive 2 over 3, right? So then it means if I want to have, like if I want to know how the function behaves in that region, it is for negative 1 over 2, which is this number, is going to be a positive 2 over 3. So which is this number, right? And then, so if I check the other part of this, like if I'm gonna check positive 1 over 2, so then if I want to have f of 1 over 2, so then I have 1 over 2 over 1 over 2 squared minus 1, which is 1 over 2 over 3 over 4, right? And then, so it's gonna be negative 3 over 4, and then it is negative 2 over 3, which is gonna be this number, so like here. So then I'll use this color. So then here and then here. So then it means if I want to graph this function in this region, so I'll have something above this horizontal asymptote. So this is horizontal asymptote. So I have something above that and something like below that. So then how would be this function? So then this function most likely behaves like this. So let's have better. So we'll have something like this. So then this function will be something like this. And I'm pretty sure the function not allowed to touch or cross these two vertical asymptotes, right? So then this is a part of graphing of a rational function. So then we'll discuss 3 steps so far. And then, so step 4. So step 4 is going to be critical points. So what a critical point is? So it is a point. So then once I have a point, so it means I have x and y coordinates for that point because it's a point on Cartesian plane. So then if so critical point is a point which the first derivative, so then critical points is the roots of the first derivative, which means f prime x equals to 0. So then all those numbers making f prime x 0. So then those numbers are critical points. However, the sign of critical points before and after those points must be changed. So then this is one of the options to find critical points. So then I call this option 1. So I also have another option to find critical points. So then if I can find so all those numbers which make the first derivative undefined, while those numbers must be in the domain of the function. So then this is option 2. So then that is option 2. So it means if I can find any roots of any of the first derivative, then those numbers could be our critical points. Or option 2, if there is no roots of the first derivative, we might have, there are probably some critical points if those numbers making my first derivative undefined. However, those numbers must be in the domain of the function, because we're looking for critical point, and then for every single point we have x and y as their coordinates. So then if x is not in the domain of the function, so then how would it be possible for any point such as critical points in the Cartesian plane? So then as an example, if I have, like, for example, f of x equals 1 over x squared plus 1. So if I calculate the first derivative, then f prime x is gonna be so if we want to have a flashback, just like for how to solve how we could calculate the derivative of any rational function. If I have u over v, if I want to calculate derivative of that, it's going to be u prime times v minus v primes times u divided by v squared. It means the derivative of the numerator multiplied by the denominator itself minus derivative of denominator multiplied by numerator itself divided by denominator squared. Okay, so then in this case, derivative of the numerator is 0 because it's a constant number, multiplied by x squared plus 1, which is denominator itself, minus derivative of the denominator, which is 2x, multiplied by numerator itself divided by x squared plus 1 squared. Then I want to check if there is any possible critical points here. So then I have to check option 1 first. So then this is option 1. So this is going to be negative 2x over x squared plus 1 squared. And then if I want to find any roots of the first derivative, then I have to set this equation equal to 0. And then as a rule, probably we know this, if I have a over b equals to 0, so then if a is 0, then a over b is going to be 0. So in another word, if I want to have a fraction equals to 0, the numerator must be 0 to make that fraction, that rational function, 0. And then in also the other option, if b is 0, then a over b is going to be undefined. So then in this case, if I want to find any possible root of this, so then I have to set this equation equal to 0. So I'm gonna have negative 2x equals to 0. So then x is gonna be 0. So then x equals to 0 could be my critical point if that number is in the domain of the function. Then so I'll check the domain of the function, then x, yes, x still valid option. So then x is gonna be my critical point, but we said for every critical point, for every single point, I need x and y coordinate. So this is x of that critical point. How would be y of that point? So then I have to plug in this x into original function. So into original function, because I want to get y coordinate of this point. So then if I plug in that number, then f is 0 is going to be 1. So then I have critical point is going to be 0 and 1. So then once I get critical point, so it means I can find the how the function behaves before and after critical point, because at critical point the slope is 0. So for any critical point, so the slope of tangent is 0. So then if that is 0, then I can find how would be the slope of tangent before and after that point. So how can I know that? So I need to create a table of sign analysis. So then I call this table of sign analysis. So then table of sign analysis. So I have this sign for critical point. So this is for critical point. So then I care about the first derivative. So then I know critical point is going to be 0, and then f prime x. So f prime x is 0 at that point. So then I'm going to have f prime x is going to be 0. Now I want to know how would be before and after that. Okay, so before that I can take any number. So as a simple option, I'm gonna take -1, and then after this I'm gonna take +1. So then -1, if I plug in this, so I have to plug in these two numbers into the first derivative. Why? Because I want to check the sign of the first derivative. How would be that sign? Is that positive or is that negative? So then if I plug in -1 here, so I'm gonna plug in this into this function. So then if I plug in -1, if x equals to -1, then I have -2 multiplied by -1 divided by -1 squared plus 1 then squared. So then -2 multiplied by -1 is going to be +2, and then -1 squared is +1 plus 1 is +2 raised to 2 is 4, which is +1 over 2. So I don't care that I don't care about the number, the value. I care about only sign. So then sign here is positive. Then if sign is positive, that means so we'll have this like this region positive. So then slope of the function before this critical point, so this is that critical point. So the function before that, so it's gonna be positive. So then it means I have something like this. And then how would be after that? So then I'm gonna check +1. So then I have if x is positive 1. So then if x is positive 1, it's going to be negative 2 multiplied by positive 1 divided by 1 squared plus 1 squared. So then it's going to be negative 2 over 4, which is negative 1 over 2. So then that is a negative number. So then it means after critical point, which is 0 and 0, 0 and 1, this is a critical point. So I have the function, the slope of the tangent after the critical point is going to be negative. So then this is all about critical points. If you need more examples, you can always, you feel free to put any comments, and then so I'm gonna explain more. So then this is all about critical points. Now, so the other thing, which is gonna be okay. So the next step, so we got 4 steps so far. So step 5. So we want to have, like, we want to find if there is any points of inflection. So then for any point of inflection, I have to calculate the second derivative, which is f double prime x. So for this also, there are 2 options. So then option 1, so if there is like all x values make f double prime x 0, so then all those are roots of f double prime x. So then those could be our point of inflection if the sign of the concavity of the function before and after that is being changed. So then this is option 1, and then option 2 is, so if any numbers making f double prime x, which is the second derivative, undefined, then those numbers could be the point of inflection if those numbers are valid numbers, which means those numbers have to be in domain of the function. Why? Because it's a point of inflection. So then if this is a point, then I have to have x and y. If I can find some numbers making the second derivative undefined while those numbers not in the domain, then those numbers not our point of inflection. So then this is like very similar story to critical point. I have like 2 options, so then I have to check all these 2 options for every single rational function. And then as the last step, which is step 6, so I have to find any x-intercept and y-intercept. So as you know, x-intercept, like to find to find x-intercept, so you have to set y equals to 0, then you're gonna find all x-intercept. For y-intercept, so then to find, then x has to be 0. So then this is, if you know all these 6 steps for every single rational function, you can graph those functions very accurate, and also you can understand how those functions behave. So then, as the last example here, so if I'm gonna give you another example here.